Sounds like it works.
Matt, you're muted. You're speaking
Sorry.
to the void.
Thank you. Yeah. Okay, so we've got some context here. We are currently running a CPU profile on for 120 seconds. We're running a sampling CPU profile on a subset of the Postgres processes. Specifically, there's one long-lived Postgres process that handles archiving WAL files. It's the parent process that spawns the extremely short-lived WAL-G processes, which is what we really care about profiling. So by default, perf is going to recursively inherit any child processes that are spawned by the PID that we're specifying here, which is how we're kind of getting away with capturing a profile of the WAL-G processes that would otherwise be too short-lived to grab by process ID. Just for context, another simpler way to do this would be to just capture a profile of everything running on CPU on this host, and then filter that as a post-processing step to just include the process IDs that we care about. But this is kind of a more direct measurement of what we want. So that's why I'm starting with it. So this is the first step of capturing the profile data. It goes to so everything else I'm going to talk about for the next couple of minutes is generic. By default, perf record is going to write out to a perf.data file, which is a raw binary capture file. To get something useful out of it, we run perf scripts. By the way, I should have started with this. Just for reference, in user local bin, we've got a set of helper scripts. Generally, you're going to want to run this one. It takes no arguments. You just run it like tab completes for all CPUs. You press enter on this, and it'll grab 60 seconds worth of profile of all processes running on the CPU, and it'll generate and it'll do all of the post-processing steps that I'm about to do manually now, just for reference. So if you're in a pinch, just run this command with no arguments, and you'll end up with a useful profile. So anyway, back to consuming this this profile run. So perf script. Don't bother trying to memorize these. It's not worth your time unless you do this a lot. So I'm going to, so perf script is going, I'm just talking in very general terms now. Perf script is going to extract the contents of that perf.data file and give us effectively a textual output of each event that was captured as part of that profiling run. I usually name these files something to indicate the context. So in this case, I'm going to say Postgres archiver. I like underscores. So this will often emit warnings. Usually you can afford to ignore them. The warnings generally are talking about how certain libraries that are on disk don't match the libraries that are actually linked, being used in the process, because we've had the library upgraded since the last time the process started. So the process is using an older version of the library, and consequently, we can't use any symbols that are available for the on-disk version of the library because they don't match what's actually being used by the process. All of that's really just kind of giving us an FYI about why some of the symbolic names for functions may be missing from the profile. So just so you can see what the profile looks like, this is not sensitive information, by the way. So this is a single event. So these are the headers, by the way, that just give kind of context for the capture. This is a single profiling event. This is another single profiling event. You can see that it, oops. Oh no, I accidentally scrolled my mouse. Let's start over. So name of the process, process ID, a timestamp, since this is second since boot with high precision. And this is the events, the CPU clock is just the default events that we were profiling. And then you've got a stack trace for for this particular process at that moment in time. WAL-G is compiled without any useful debug symbols, unfortunately, which means we don't get symbolic names. All we get are the raw virtual addresses for the frames in the stack trace, which makes it hard to interpret. So we won't get a useful flame graph, but I'm still going to generate a flame graph so you can see what it looks like. What I really want is this raw profiling data, so we can look at effectively a timeline to see when the WAL-G processes were hot on the CPU. Okay, so stack collapse. And then use the same name, but change its suffix.
And as a side note, this is what the script, the helper script in user local bin is doing internally as well.
And it's just a shell script, by the way, so you can totally see what it's up to. Here's the perf record and the perf scripts and the bits you just saw. Okay, so we're going to log out. Oh, what do I have as a stop stub? Oh yeah, right. That's okay. That was from that other incident that's less interesting than this one. So I'm going to copy both of those files to my local machine. This is that textual output that we were talking about, and this is the flame graph that we generated from it. So the flame graph you can open in any JavaScript enabled browser. And if you haven't played with flame graphs before, this is definitely worth showing. So it's SVG files or scalable vector graphics files. They're graphic images, but they're effectively, unlike most image files, these are actual text files. These are XML files, and they include some helpful JavaScript that lets you basically treat them as interactive graphics. So we can do mouse overs. Look at the bottom of the screen here. You can do mouse overs for each frame. And it'll tell you things like sample count and the percentage of sample counts. And you can also do things like search for all frames containing a particular string, which is not super useful here since we don't have any useful function names, but in general, it's going to be more helpful. So the takeaway here is we were profiling the Postgres archiver process and any child processes that it creates. So this frame over here that represents 1.3% of the samples was the Postgres process, and 98.7% of the samples came from WAL-G child processes that were spawned by it. So we know that that most of the CPU time that we're observing here came from WAL-G, not from the Postgres, the Postgres parent process that was spawning them. So because that's the case, I'm going to just...
Go ahead.
I was just going to say, go ahead, Igor.
And this is CPU time. It's sampling on CPU time. I just want to highlight that and make that explicit.
Yes. Yeah. Super important. Yeah, this is just CPU time, not wall clock time. What we really care about in this case is wall clock time, and we're using CPU, and so bear that in mind as we look through this. This is not going to represent time spent on disk I/O or network I/O. Okay, so what I wanted to use the same profiling data for is to load it into another tool called Flame Scope, which will give us a timeline of when these samples occurred. It's just a convenient way to visualize. It's a convenient way to visualize. Wait a minute. Yeah. Okay. To visualize when we had on CPU time. What's your name?
And visualize that over time. So the
Yes.
The thing worth noting here is when you look at a flame graph that is averaged across the entire duration of the profile. So this was a 2-minute profile, right? which means what we were seeing was sort of the average across those 2 minutes. That doesn't tell you anything about the time dimension. And so what we're about to see, what Matt is about to show in Flamescope is actually showing that time dimension. And I'll hand it over to you for further commentary, Matt.
Sure, yeah. So this is what Igor was just talking about. You can see we've got bursty behavior here. This is what we would expect from what we know about the processing model, that we should have bursty behavior. By the way, when I was talking earlier about how little of the time was spent in the Postgres process, the main reason I was mentioning that is we could potentially, as a kind of an in-between post-processing step, pull out only the samples that came from the WAL-G PIDs rather and throw away the samples that came from Postgres. But because they represent such a small percentage of the samples anyway, I'm going to just skip over that and assume that rightly assume that the large majority of what we're looking at here came from WAL-G, not from Postgres. So that's the whole reason I wanted to show the flame graph. So yeah, so what we see here is an oscillating pattern where we spend some significant time on CPU and then a lot of time not on CPU. And the time that's spent not on CPU could be spent in any of a few possible areas. One is disk I/O reading the WAL files. Another is network I/O interacting with the API for uploading to the object storage bucket. And another is just not doing anything, waiting for another. So this is a little bit harder. I feel like a whiteboard would do better for this. So the operating model for WAL-G's background upload behavior. So Igor already knows about this because we talked about it yesterday during the code review. But I wanted to kind of revisit. Sorry, I'm making gestures, but you can't see it because the gestures don't really tell you anything anyway. I guess the important piece here is, oh, maybe I could just use a text file for this. Yeah, I'll do that. Okay. So the sequence of events for any individual invocation of WAL-G. So WAL-G gets invoked. Take a step back. Postgres will run its configured archive command once per WAL file that needs to be archived. We know that we've got a backlog of thousands of WAL files, so this is going to run thousands of times eventually. And we just saw that we generate about 5 or so WAL files per second. So that should be about approximately the call rate for this archive command. So our archive command is a thin shell script wrapping an invocation of WAL-G WAL-push, which means we invoke a new WAL-G process about 5 times a second if we're keeping up. Am I remembering the numbers right? It was about five files per second that we were generating.
Yep.
Okay.
Yeah. So I think 4 or 5.
4 or 5.
Range,
yeah. Okay.
Yeah.
Okay, great. So just so going with that, we would expect to be able to keep up. We'd expect the average duration for the WAL-G invocation, for each WAL-G invocation, to need to be about 1/5 of a second, about 200 milliseconds. So those are very short-lived processes. This should be very short-lived processes. But WAL-G has this interesting kind of implicit batching behavior where it gets WAL-G WAL. So you'll have one WAL-G WAL process get invoked with a particular whatever. I'm going to make up the file names, and it will implicitly say, okay, I'm going to on my main thread, I'm going to archive. I'm going to start archiving that specified WAL file. And as a background activity, I'm also going to try to look for the next several WAL files. And this count is configurable, and we've just increased that count from 10 to 15 yesterday, which was the change issue that Alexander made for us. And we're, so I know I'm covering ground that you'll have some pieces of, so I just wanted to make sure we're all on the same page about the line diagram I'm about to try to draw. If it takes slightly less time to complete this file, that thread will pick up another file before the end of the main thread finishing this one. And that file can potentially go on for about the same amount of time because all these files are roughly the same size and should be approximately the same amount of work to do an upload for, right? So statistically, we would expect about half of these threads to finish before the main thread and half of them to finish after the main thread, because they all get to start their work at about the same time and they all have about the same amount of work to do. So when a thread finishes early, like this example, then it gets to grab a second file to work on. And when it finishes late, whenever this first line finishes, it says, okay, all my helper threads, you're not allowed to take any more work, but you are allowed to finish what you're already doing. And so because they all tend to have about the same amount of work to start with, I would expect that each of these helper threads gets to do either one file or two files, never more or less. Probably never more or less, and there may be some other influences that can affect. I'm not as confident about the less, but I think it would be really surprising if any of the threads got to do. Sorry, when I say threads, I mean Go routines, but kind of threads is more natural to talk about for some reason. Anyway, sorry, I digress. The whole reason I'm mentioning this is in this case, I'm going to elide the rest of these. In this case, which I think is because we've got 10 or 15 now of these helper threads, it's very, very likely that at least one of them is going to get to start a second file, which means that our average duration for completing this command is going to be twice as long as it takes to upload just the one file, because we would expect at least one of those threads to have just barely started its second file by the time the first file finishes. Does that reasoning hold water for all of you?
I mean, this is good.
I think my audio cut out for a second. Can you say that again?
No, I mean, this is good. I mean, I'm.
Oh, okay.
All the threads which started, it will wait for all of the threads to complete first, right?
Yes.
And then it will. And when archive command fires again in between, will it?
Oh, that's a great question. So the Postgres archiver will only run one archive command at a time. And so these invocations are serialized, and this is the other interesting part of the story. So the next time the archive command runs, it's going to say run for this file, and WAL-G will complete. So that there's kind of so there's kind of this oscillation between WAL-G having a lot of work to do, where it uploads the one file that it was asked to upload, plus an indeterminate number of additional files, thanks to these helper threads. When these helper threads finish, let's just say this is 02. So later on, the next time the Postgres archiver says, hey, I want you to archive this file, this WAL-G process is going to say, oh, you know what? I've already uploaded this file. So I exit almost instantly. Does that make sense? This is going to be a lot easier to see. This is probably worth showing real quick. So because on these nodes we have our BPF tools, we can do a quick exec snoop on this.
Yeah, you had a really nice demo of this. We were looking at this yesterday.
Cool. So I want, make sure I spell the options correctly first. So I want timestamps for reference, and I want process name to be WAL-G. So what this is going to do is this BPF tool is, I'll press enter in a second, but this BPF tool is going to attach to the exec VE syscall and a couple of other, I think at least one other variant. Anyway, the point of it is whenever a new process gets created, this BPF program is going to capture the event of creating that new process. check to see if the process's name matches what we've specified here, and then print out basically a log event so we can see it. And I'm going to press enter now, and you'll see the pattern. So it takes a couple of seconds to compile and install. And so now we're running. So I'm going to press enter now, and press enter as soon as this batch finishes, just to kind of give a visual break. Okay, now we'll stop running the program and talk about what we just saw. So most of these invocations of WAL-G are very, very quick, and you can see that we're getting the sequential WAL file names here. When I say quick, I mean they're finishing in a few milliseconds each, a few tens of milliseconds each. And what's going on here is WAL-G says, oh, you know what, you're asking me to upload this file, but I can see from my scratch notes that I've already uploaded the file. So I'm just going to exit immediately rather than doing any real work. So this is effectively a no-up run. Eventually, it gets to the end of the list of files that it's already uploaded on this occasion. And so it says, oh, I haven't uploaded this file. Okay, I'll actually do some work. And by the way, I'm going to launch I'm going to launch my helper threads because I can see that I have a backlog, to proactively upload another big old batch of files. And that's why this invocation takes several seconds to run. In this case, it took just under 3 seconds to run. And then the next n invocations again are, oh, I see this file's already been uploaded. I'll just exit immediately. So this is the first kind of layer of interesting oscillating patterns that you'll see, where n out of 1 runs are going to be very quick because they're no ups, and the 1 out of every n runs is going to be rather slow because it's actually doing work.
Right, and basically for each one of these groups or batches, the first item is the slow run. Actually, I guess it would be the next one, right?
So this is start time. Yeah, keep going.
It's start time. Yes. Yeah. Okay. Yes. Yeah. Yeah. Okay. Yeah. Mm-hmm. So BE in this case is going to be the slow run, mm-hmm. and all of the fast ones following it are the concurrent, optimistically concurrent WAL files that were uploaded by that first one that are now sort of getting no-opt.
Mm-hmm. Yep. So this one definitely uploaded BE, but it also secretly, silently uploaded BF and C0 and C1, et cetera, on all the way up to D1. And the number of files in the batch that this one kind of secretly did for us is what we were trying to increase by increasing the WAL-G upload concurrency setting. Just because it's kind of neat to actually see the concrete pieces of this. This is the directory. This is the directory where it kind of keeps track of which files it's uploaded in the background. So if we just run this in a loop, refreshing every 10 seconds, you can see that these files are very short-lived. So the exec snoop that we did was showing us the typical batch size implicitly by showing us that we had I should have counted them, but it was
15.
Yeah. Yeah, it was about 15-ish. Yeah, and so we'll effectively get all 15 of those will have corresponding 0-byte files added to this directory, and then the subsequent runs of WAL-G will look in this directory before they do any work, see that file name already exists, and know that file was already successfully uploaded to the object storage bucket. So that's the mechanism by which it'll figure out that it can treat itself as a no-up run. And we can, just by watching files being created and destroyed from this directory, we can kind of see the pattern of that happening. So that was the last bit of show and tell I wanted to give. This is all not obvious behavior. I don't even know if this is documented. I came across this a few months ago during our previous round of WAL-G throughput improvements. Yeah. So tying that back to tying that back to the Flamescope data. Now, with that context, we can see that that these periods, by the way, the scale for this is each vertical line represents 1 second of data, and we captured 120 seconds worth of data. So this time span is probably about half a second of CPU intensive activity. And we don't know what it was actually doing on CPU during this time because we don't have symbolic names for any of the functions. If we did, we could actually take a peek at what they were by highlighting that section and getting a flame graph for it. But because we don't have symbols in our WAL-G binary, it's all we get is just unknown, 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 all the way up the stack. Yeah. So this is part of what I wanted to see is when we're having these microbursts of CPU activity, how many CPUs are we using? And the answer to that question appears to be, if we mouse over, we can see how many samples there were in. Sorry, this is also kind of not obvious. Each second is broken down into 50 buckets. I'm going to switch this to 99 buckets because that was our sampling rate. And so at this point, we'll see for each sample how many. For each point in time when we captured a profile, how many stacks did we grab? And we'll only grab a stack if a thread is on CPU at that time. So this is effectively saying how many CPU cores was WAL-G using at that moment in time. And we can see that the scale here goes from 0 to 16, which implies that at least for very brief periods of time, for at least occasionally, WAL-G is consuming 16 CPU cores, which is rather a lot, but it doesn't do so for very long. And we've got 96 CPU cores available. And generally we're using a little bit more than half of them during the workday peak, I think. I think it generally rises to about 50 to 60% usage, if I remember right.
Yeah, that's my recollection as well, yeah.
Cool, so yeah, so that means that we can afford to burn 16 CPUs in short periods of time doing WAL archiving. So this also kind of suggests that sorry, taking a step back, there were two things I wanted to get to see with this profile. One of them was to see how long these. I knew that these bursts had to be happening, but I didn't know how long they were happening. We saw from the exec snoop that the ignoring the no-op runs that we've got up here. For the runs that actually did work, we knew that they were taking. I think before we made our tuning change yesterday, we saw an example of it taking a little bit less than 3 seconds, and now they're taking, at least in this case, it took about 3 seconds. What were the other ones?
Wall clock time, that is.
Yeah, thank you, wall clock time. So that means, and this is representing CPU time. So if we say, for example, three columns here, since we've got 1 column per second, 3 columns here would represent the total wall clock time for any single WAL-G execution. And it kind of looks just at a glance like maybe, much less than 3 seconds of that was spent on CPU, which means that the rest of that 3 seconds was spent off CPU, probably doing either disk IO or network IO. But that's I mean, rationally, those are places you would expect WAL-G to spend a significant amount of time, on, but I don't actually know. I guess right. Furthermore, I would expect some of those threads to be idle and some of them to not be idle.
Yeah, and that also on a high level matches what we see when we look at the overall CPU utilization in top or PIDstat.
Yeah,
you were showing it earlier. So it's what is it peaking to? WAL-G peaking to like.
Let's just switch to PIDstat.
Yeah, PIDstat can tell us that a little bit.
let's see.
more
I never
clearly.
remember the
But
implications.
when I ran this yesterday before we did our tuning, it was peaking, I think, up to 400 or 500%.
Yeah.
So that's
is it capital
10,
G?
I can never remember. Yes.
And then we'll do 1 second intervals.
Yes. Yes. So it's, yeah, we can see now it's bursting up to, I mean, it is very bursty, but it's bursting up to like 600%. So 6 cores, but we gave it 15 go routines, right?
Yes.
So it's using roughly half of those go routines on CPU. And that matches what we were just looking at, and sort of this idea that during these bursts, we're not spending all of that time on CPU. We're also spending some of that time waiting. So I just wanted to kind of tie that together as well.
Yes. So all of this is kind of tying into the overall question of is it safe to further increase this parameter? And the answer appears to be yes. We can moderately increase it again. Is my takeaway. And I'm thinking the way I think this is the same way that we're all framing it, but just to be explicit, in terms of machine resource usage, we're looking at CPU usage. Memory usage is less of a concern, but memory thrashing could be a concern. I checked yesterday, and it seems to be perfectly fine with respect to that. So I'm going to gloss that over for now without rechecking it. Disk and network I/O are the other two machine resources that we could be concerned about. I am super not worried about disk I/O as a concern for this host. We are nowhere near, like, we're using about half of our spec capacity on disk I/O, and there's no way WAL-G can burn through that. And so that leaves network I/O, and as I recall, it's harder to calculate our actual networks, our actual network usage, because disk I/O counts against it as well. But last I checked, we were also nowhere near capacity on that as well. And I kind of don't see, I kind of don't see WAL-G being a significant risk for that as well. So those are kind of the categories that we could focus on. And so far we're focusing
Can I interrupt you for
on
the disk
CPU.
I/O?
Yes, of course, go for it.
Sorry. Yeah, I'm not always right with my assumptions, but even if we would take out all throttles and let WAL-G run full powered with as many threads as we go, I now would propose, no, not propose, I would assume that the disk I/O may go down because the fresh WAL files are always in the memory. So you don't have to read them from disk anyway,
Yes.
because if they are fresh, they are already in the memory. So the disk I/O might even decrease if you are fast with shipping out these files.
Yes, yeah, you're spot on. We only have to worry about physical disk I/O when we have a backlog like this.
Yes.
So if we can keep up, then we don't need to worry about that at all.
It's the whole swapping problem when you started.
Yep, totally agree. So I guess, okay, so in terms of tuning, those are I think it's viable to bump that knob a little further if we want to. For potential, okay, so we have a couple of other things that we can do for not necessarily immediately, but I think for what's the right way to talk about this? We know that we have some kinds of events that can trigger a significant increase in WAL generation rates. Like, for example, when we do bulk data changes, like for migrating from 4-byte integers to 8-byte integers for our primary keys, just as an example. Anything that does large bulk data updates that ends up writing historical blocks in particular is going to generate more WAL files than more WAL records than we usually get. We're not at the end of needing to do that kind of maintenance. So I'm a little bit worried that we're going to have, future, perhaps ongoing and future background migrations that kind of nudge us over the edge. And I guess kind of in an even more mundane sense, folks doing feature development work are not thinking about, WAL generation as a design requirement. So the fact, like Alexander said to start with, we have, I think, pretty strong evidence at this point that we are kind of continuously right at the edge of saturation for being able to archive these WAL files. Turning this knob further gives us, kind of, I mean, I think we're effectively adding maybe 10%. It's giving us a small additional margin, and I'm kind of worried that that's not going to be enough to last us very long. Maybe weeks, maybe months. So I kind of wanted to talk about some of the other possibilities in addition to what we're already talking about doing. So we, at the start of this conversation, we talked kind of briefly about moving the CI tables to their own database cluster, and I think that's very much a game changer in terms of separating two large drivers for read and write activity. So I think once that's completed, we'll probably be in a very different space. But I kind of don't feel like it's reasonable to just assume that will take care of our problems. I don't know what the timeline is for that, and I kind of don't feel like it's reasonable to. I feel like I'm using too strong language here. I feel like it's a significant risk to assume that project will complete.
We shouldn't put all our eggs in that basket.
Thank you. Yes, that's so much more concise. Absolutely. So that's my feeling, but I wanted to see how the rest of you felt about it. Because again, I'm not keeping up with the pacing for that project.
Okay, first of all, it can be that I have to leave in for a few minutes, because we get some chairs delivered via a semi-truck.
By the way, since I think we've covered the interesting demo part, I'm going to stop the recording here if that's all right.
Yeah, I think that's a good idea.